This mini lecture is about geologic maps and the conventions that we use when we make them. So what is a geologic map? A geologic map is showing you the bedrock that is under your feet or under the parking lot or under the river or whatever happens to be at the surface. It's showing you the rock that's underneath there. And one of the cool things about geologic maps is they're very colorful. There are conventions for how geologic maps are made and colored, and we're going to talk about them now. So let's talk about the color first. The colors indicate rock units, and a rock unit or formation is more than just one layer commonly, but it is a group of rock that's continuous in time that formed in a specific environment. Everywhere on a map that is the same color is the same rock unit. Now, in addition to color, geologists also use symbols to tell you the names of the rock units and their ages. Their symbol is usually 2 to 3 letters, and the first letter is commonly the age of the rock. Usually we use the first letter of the geologic age to do that. For example, Devonian is a capital D. But there are a lot of C ages, and so Cretaceous is a K. So number 1, KJM, is a Cretaceous age rock called the Joaquin Miller Sandstone, and that information would be found in the key. The second arrow is pointing to KS, another Cretaceous age rock. This one is shale. And the third arrow just has a lowercase gb. So that's showing you a gabbro of uncertain age. They haven't told you the age of it on this geologic map because they're not quite sure what the age is. Remember the geologic timescale. There are some common conventions with color. They're not used in every map, but very commonly, yellows, oranges, and reds are used for Cenozoic rocks. Greens are Mesozoic rocks, blues are Paleozoic rocks, and purples, browns, and pinks are used for the oldest Precambrian rocks. The other thing that the geologic map shows are lines, lots of lines, and many of those lines are what are called contacts. And contacts are the boundary between two rock units. Number 4 here is pointing to a boundary between a mossy green and a brighter green interlayered rocks on this part of the map. The solid line indicates that the geologist who did the mapping stood there on the contact and knows exactly where it is. Contrast that with the arrow where 7 is pointing, and you see the boundary between two different colors is marked by a dashed line. That means that the geologist couldn't observe it right there for whatever reason. Maybe there were plants there, or something was in the way, or the land wasn't accessible. Now, number 8 is pointing to a dashed line that cuts across rock units. This is a fault that the geologist can trace on one side or the other, but it's buried under these Q sediments. Q units on rocks are usually loose gravel that's been deposited by a river or that sort of thing, very young rocks. Faults are also shown on a geologic map, and faults show up as generally straighter lines, not always perfectly straight, but commonly straight, like you see in number 5, a heavy dark line where the rock has moved on one side relative to the other. The faults are sometimes marked with the direction of movement if that can be seen, so you might see a strike-slip fault with arrows pointing in opposite directions, or a normal fault with a D and a U indicating up and down. Or you might see something like you see there with the number 9 pointing to it, with teeth on one side. A fault marked with teeth on one side is a reverse or thrust fault, and the side that the teeth are on is the older rock that's being pushed up on top of the younger rock. So the purple rock here is coming up on top of the light green rock. Rocks also get folded, and when folds are shown on maps, they are sometimes shown with a fold hinge and a set of arrows. An anticline would have arrows pointing away from the hinge, and a syncline would have arrows pointing towards the hinge, and you can see that in number 6, a dashed line down the middle of this little round piece of TV. And if you look really closely right above the 68, you'll see arrows pointing towards each other. So this is a syncline. It's a little basin kind of thing right here, um, marked on this map with the number 6. Next to it, with all of this swirly lines, those are many folds, again and again and again. In this case, the fold hinges are not marked, but you could pick out where they are. They're right in the middle of where those folds bend over each other. Here is that map again. This is from Pennsylvania, by the way. The green box is surrounding one fold. The red box is surrounding another fold. And you can see that the same rocks are showing up in both places. So if this is a syncline in green, then it's also a syncline in red, with the pink rock in the middle and then orange and green going towards the outside. If it is two synclines, there has to be an anticline in between. And so on the uncircled part of the map is the anticline area. Now, the other thing that geologic maps very commonly show is the actual orientation of the rock in space. Remember strike and dip, which we looked at when we were playing around with the clay, and that symbol on the map looks like this little bar and dash that the number 10 is pointing to. You can see the longer line marks the direction of the strike, and the shorter line marks the direction of the dip, and the number marks the amount of dip. So this is a bed here that the geologist has measured that's dipping 55 degrees towards the southwest. So let's look at this geologic map. You can see the layers of greens and blues and yellows, and they mostly follow the topography, right? So because they mostly follow the topography, the same shape as the stream beds, we know that these must be fairly flat layers. And these, of course, are very tightly folded. And this is something that's sliced up by a whole lot of faults. So you see colors coming together along straight lines, no indication of anything folded here. And so this is a geologic map of a very strikingly faulted area. So let's just take a quick look at this strike and dip symbol and imagine says it's dipping 70 degrees to the north, right? So let's say you're standing on the red X and you are looking to the east, and what are you going to see if you look at that? What does 70 degrees dipping to the north look like? Well, here's a sketch of what that would look like. Very steeply bedded units where the angle is 70 degrees from the horizontal to the top of the bed. Very steep units dipping towards the north. So a geologic map is very useful. If you know how to read it, you can imagine what a picture of what those rocks will look like.